Okay. Hello, everyone. Thanks for tuning in to today's Corundum developer meeting. So first off, just go through announcements and then status updates. The next Corundum developer meeting will be in 2 weeks on July 31st, and the next Switch developer meeting will be next week on July 24th. Right. Okay. And then moving on to the status updates, I don't have all that much to discuss today. I put some more changes up to the main upstream Git repository for Corundum. I'm going to go over those changes in a little bit more detail here on the next couple of slides. Then I've been doing some work on the Mac control and PFC components to support PFC and pause frames in Corundum. And then also some of that's going to be integrated into the Macs in the Verilog Ethernet repository as well. And then I've made a couple changes to the Verilog Ethernet that I'll talk about at the end. So not a whole lot of stuff to discuss, but let's get into it. All right, so I've updated the GitHub repository with a handful of changes. A couple of these are pretty straightforward, but a couple of them are a little bit more complex. So first one is we got some changes from the guys at Missing Electronics to fix some of the SFP interface code. The idea is that most of the modules use I2C address 50, but there's some of them that use, I think it was I2C address 51. Why? I'm not exactly sure, but that's what they do. So we have to make a few modifications to the driver to support that. I think it's maybe a little bit hackish, but it seems to work pretty well. And I guess the idea is that eventually, when we move this into management softcore, then that'll be cleaned up a little bit. One thing I will say is that I don't know if we're going to be able to do this, or if we're going to be able to support this on all of the dev boards. Anything where we have direct access to I2C, it should work. But on some of the Alveo boards and whatnot, where there's a board management microcontroller sitting in line with I2C, we might not be able to access address 51. So we'll see. But the way it's set up right now seems to work okay through the Linux I2C stack anyway. All right, the next point down here is another fix from MLE for improving the RX buffer allocation and error handling, or the RX buffer allocation error handling. And I guess the idea here is that if the allocation of buffers fails on RX, then it can actually clean up after that better and present, I think, a few useful log messages for what to do in that case, what settings to try adjusting to resolve the issue. And then Emily also had some ideas about using dynamic debug. So replacing a couple of the well, they were interested in one print K specifically, well, not print K, but netdev info call. Replacing that for a debug level call, which is disabled by default, and then using the Linux kernel dynamic debug, you can turn that back on. So I pulled that in and then also flipped a few other calls as well over to debug, and also added a script so you can relatively easily turn some of these things back on through dynamic debug. So that should hopefully clean up the output and demessage quite a bit. So you shouldn't be getting stuff during normal operation, only stuff during initialization, and then if anything fails, you'll get, hopefully prints about that. But if you're just sending and receiving packets normally, even if queues fill up or whatever, all those messages should now be debug messages. Then the three main changes that people should be aware of, especially if you're using like an out-of-tree driver, I did a bunch of reorganizing of the queue control registers. And this is basically a stepping stone towards some of the, new control, queue control logic that I've been putting together. So I just wanted to get this off my plate and get it in the repository, so I don't need to keep rebasing it all the time. But the idea with this is we're well, I'll talk more on the next couple of slides, but it increases the density of the completion queues and event queues, and also changes up the register layout a little bit to be a bit more forward-looking in terms of what we want to do going forward. So should make things easier to support once we get some of the more extensive rewrites of the queue management squared away. The next thing I did is CQ consolidation. So previously we have two different completion queue types. We have TX completion queues and RX completion queues, but that are exactly the same effectively. So it doesn't make sense to have two different queue types. If we roll that all into one, it can simplify the logic a little bit and also simplify, how the driver is handling things. Now that we have the dynamic queue allocation support in the driver, we can have a single queue type for completion queues, and that'll simplify things. So I went ahead and implemented that as well. And then finally, another thing I did, I actually don't think this affects the software interface at all, is I peeled off the completion and event handling logic into, well, right now it's the same module, but just two separate instances. But the idea behind this is you could use different logic going forward for each of these. I'll talk about that a little bit more in a minute. I also updated the Vivado make files. I know there was an issue where Vivado updates its project file periodically, and that was during the build process, like during bit file generation. I think it's updated during the implementation run, it gets updated, and this was screwing up the make file. So you'd run make, and then you'd run make program, and it would try to resynthesize the thing. So I think I have this fixed such that, if you change the source file, it'll still do all the correct things. But if anybody's running into any other issues with that, let me know, and I'll see if I can sort it out. But I've gone ahead and updated that in the repository because with the testing I did, it seemed to be doing what it was supposed to do. So yeah, if anybody has any problems with that, let me know. All right. So moving on to some of the queue management stuff in a little bit more detail. So like I said, there's three main changes. First one is the queue control register reorganization. And I guess I also coupled this with some driver refactoring as well. So previously I used head and tail for the pointers into all of the queues. And unfortunately, that's a little bit ambiguous because do you NQ at the head and DQ at the tail, or is it the other way around? It's you could interpret that either way potentially. So I replaced that with producer and consumer. So the producer, that's doing the enqueuing, the consumer, that's doing the DQing. Much more straightforward. And I think I made a couple other tweaks as well. But then I also changed the register layout for all of the queue control registers. So this one, we're doing kind of two main things. One of them is that we're adding these encoded commands that you write to some of the registers instead of doing kind of normal bit manipulation where you might, read the register value, flip a couple bits, write it back, or have some idea of what all the bits need to be, so you can just do a blind write and update the state. Instead of doing that, we have these atomic commands where you just do a single 32-bit write, and it will set or clear a single bit, or set a bit field or whatever. So that should make things a little bit easier to work with. And it also doesn't really have much impact on the logic utilization on the FPGA side as well, because with the queue management stuff, we were already repacking everything into the internal RAM. So, we're just kind of looking at different bits to do the same thing. The other thing I did is doubled the EQ and CQ control register density. The idea going forward is that we're going to replace the RX and TX queues in queue pairs. And if you say take your available register space, you cut it in half. If you can implement n queue pairs and 2n CQs, that's like optimal, because then you can have one CQ for every send queue and every receive queue in the queue pairs. So gone ahead and done that, and seems to work fine. Again, it's just a reorganization, so it doesn't really make that much difference. And then CQ consolidation, again, with this one, we're consolidating the RX and TX completion queue types into a single queue type. So we only have a single queue manager for all of the completion queues. And then, right, I also separated the completion event handling. So the Reasoning behind this is it does a couple of things. One of them, it allows you to use different logic for doing the event write back and the completion write back. And point behind this is that we want to do potentially a more complicated completion write back module that supports batching. So it'll queue up several completions to write back, buffer them in its internal memory, and then dump them out all at once with a single PCIe write. And we don't necessarily want to do that with the events. So if we have two separate modules, then that's going to make that implementation more straightforward. Another thing is that there's a potential, deadlock that can occur if the completions are what are generating the events. So when you enqueue a completion into a completion queue, that can generate an event. And then that event, if that's getting processed by the same logic, if that logic is exerting back pressure for some reason, then you could run into a situation where you generate an event, but then you can't actually generate the event because there's back pressure. And back pressure is because there's no space for, a new event. So that won't resolve itself until, that I think I was running into some issues with that with some of the rewrites that I was doing on the completion queue handling logic. So that's an important thing to fix. Oh, I guess another thing I should mention in relation to that is that the updated queue management logic, the other component of that is not to generate the events immediately, but to defer the event generation to basically do some interrupt coalescing, but at the level of the events. Don't necessarily want to do that again with the events that are being written out into host memory. You might want to just fire those off immediately and then fire off the interrupts such that you can start handling stuff. Instead of having a second layer of interrupt coalescing that's just going to slow things down. And since you're deferring the generation of the event, that exacerbates the deadlock situation, because you could have your entire internal memory filled up with completion queues that are all, geared up to fire off an event. As soon as you start firing off those events, then you have to clear out entries in the internal state to process those events and write them out, and that can result in the in this deadlock condition. So I think with the current setup, it's not really an issue, but with the new one, this is something that that we need to avoid. So logic resource utilization, I think it's similar with all of these changes. With the CQ consolidation, I do know that that one's a little bit less than ideal, because we're basically using double the number of queues for the CQs. So if the TXQ and RXQ counts are similar, then the CQ count, is similar. But I think a lot of the designs use like 8192 TXQs and 256 RXQs, so that you end up with 16384 CQs, which is not great. But I guess with the dynamic queue management, we could probably adjust that, because if we just take a byte of 256 out of the available transmit queues effectively for the receive queues, that shouldn't be, I think, a major problem, especially with all the dynamic queue management stuff. But that would be a relatively simple change just at the config.tcl level. We don't need to change any Verilog to determine how many CQs are generated. So that being said, it does use a few more block grams for the completion queues, but it doesn't seem to make a huge deal of difference with the timing performance and whatnot, at least with the test synthesis stuff that I've done so far. So that about rounds it out for the high level. I'm going to just very quickly go over what the new register format looks like for anybody that has an out-of-tree driver and needs to make some adjustments. So for the queue control registers, for the CQ and the EQ, it looks like this. We've basically packed everything together into 16 bytes. The other change that I'm making as well is I'm knocking off the lower 12 bits of the address field, such that we have space for a VF ID number. So right now the VFID number that is not implemented, but that's going to be a to-do once we start looking at getting SRIOV operational down the road. So that means everything has to be all the rings have to be 4K aligned, which I think is reasonable. Yeah, so the ring base address, we got the lower 20 bits in the first register, the upper 32 bits in the second register, and then third register has the control and status bits and the event queue number or IRQ number, depending on whether it is a completion queue or an event queue. And then the final register here has the pointers, the consumer pointer and the producer pointer. So the advantages here, it's 16 bytes, so we can double the number of CQs and EQs in the same register space. And we're also using atomic commands to change the queue state. So with things like updating the pointers, arming and disarming the queue, that sort of thing, instead of doing some sort of a read, modify, write operation on the control register, you can just write an encoded command that says arm the queue, and it'll arm the queue. Or you can also do fun stuff like combined pointer update and arm. So the hardware supports that. I don't actually have it implemented in the driver yet because of just the way the code is put together. At some point, perhaps we can implement that and save a few more MMIO writes to rearm everything. So that's what that looks like for the CQs and the EQs. For the TXQ and RXQ, it's similar. I made a couple of small modifications though. The control and status register, that's a full 32 bits. And then I have a separate register with the CQN, then the completion queue number, and then also the size. So it takes up a little bit more space. And the idea going forward, this is not implemented yet, but the idea behind this layout is that the last three registers can be duplicated to make a queue pair. And with the queue pairs, you're basically amortizing this big honkin' base address register across both the transmit side and the receive side to make everything a little bit more efficient. So far, we're just implementing part of that for the TXQs and the RXQs. Later on, once some of the logic has been rewritten, we will switch over to using this layout. And then just very briefly, this is what the commands look like. I think the VFID command is not implemented yet, but all the other ones should be. So we have command to set the size, command to set the CQN, EQN, or IRQN, set producer pointer, set consumer pointer and arm, set enable, set arm. The idea is that you can take any of these and write them to basically anything other than the base address register. So for the TXQ and RXQ, any of these three registers, config, status, config, or pointers, and then for the CQ and the EQ, either the config or the control status or the pointers registers, either of those will accept these commands. So the upper portion defines what the operation is, the lower portion is the argument. So the idea is you don't need to do any bit shifting when you're putting these together. You could just take your new producer pointer or consumer pointer, mask it off, and or it with the most significant bits here to generate the value to write to the register. So keeps things relatively simple. All right, so that's about all there is to say on that front. Again, if you have a out of tree driver, it'll need to be updated to support these new register layouts. Okay, so moving on to the MAC control and pause frame stuff that I've been working on. So for those of you not familiar, the MAC control layer is part of IEEE spec. The idea is it exchanges messages between Macs. So not between the software running on the host or anywhere else in the stack, it's between the MAC layer itself. And this is used for a couple of different things, but one of the main things is PFC and pause frames. So for those of you not familiar, PFC and pause frames is hardware flow control for Ethernet. The idea is that the receive side can request that the transmit side of the Mac sends a frame to stop transmission when receive buffers are filling up. And then at the other end of the link, the packet will show up, and then it's supposed to block transmission of new frames to prevent the buffer at the other end of the link from overflowing. So PFC gives you several different priority levels that can be paused independently. Pause frames just pause the whole link. So yeah, obviously they have some trade-offs between, which one you might want to use for a given situation. So the PFC and pause frame support, the idea is to generate and handle PFC and pause frames using the Mac control layer components. Now I'm trying to put this together in a relatively flexible way such that it can be either integrated into a Mac module itself, which I will be doing with the Macs in the Verilog Ethernet repository. And then you can also integrate it into Corundum directly, independent of the Mac. And then in that case, it'll sit in the L2 ingress and egress modules in Corundum. So status at this point is mostly implemented. Everything seems to be working fine in simulation. There are a few odds and ends I'm still getting squared away in terms of some of the interfacing and Mac integration. And I also need to add a couple additional status signals that might be useful for connecting to the statistics subsystem and whatnot. So the Mac control layer, a little bit more details on that. Like I said, this exchanges Mac control messages. Those messages are basically normal Ethernet packets that have standard multicast destination address and ether type that can then be used on the other end to extract to identify those frames and extract the payloads for processing. So on the TX side, what we need to do is inject control frames after the transmit FIFO. You got to do that for latency reasons. The whole point of this is flow control. If we have to wait behind a bunch of other stuff in the TX FIFO, then it kind of becomes less effective. So the module for the Mac control layer has to serialize the header and all of the parameters in a way that all the fields can be customized, and then arbitrate between that and the actual data to transmit with a priority arbiter. The idea being that the Mac control frames can be sent at a higher priority such that if there's currently a data frame being sent, as soon as that's done, then we can fire off the control frame before resuming data transmission. Obviously, we want to reduce the delay to make sure that the flow control is as effective as possible. But since we have this arbitration logic, we can also in a pretty straightforward manner support pausing the flow of TX data just by adding another input to that arbiter in a way that the control frames are not also affected. So if we assert that pause request input, then we can just directly block the flow of data leaving the Mac. So the nice thing about this is it means that you can, in a relatively straightforward way, actually terminate the receive side of pause frames without having to have the user logic sitting behind the Mac do anything. Just internally, the Mac will shut itself off in the transmit direction. On the RX side, we need to extract control frames before the RX FIFO. Same reason on the TX side, we want to make sure that we're not dependent on what that FIFO is doing, and we don't suffer any delay going through the FIFO. The other thing is if that FIFO is full and it's dropping stuff, well, we still want to be able to receive the control frames. So the RX side has to filter on the source, destination, ether type, and opcode. You don't necessarily have to filter on all of those. You might not want to filter on the source, but dest, ether type, and potentially opcode are, I think, going to be normal things to filter on. Then it needs to extract the header and parameters and hand those off for processing. The other thing is that as the module is not set up to buffer the control frames that are coming through, so when it identifies a frame as being a control frame, well, it's already handed off most of the frame to through the receive side of the Mac. So the only thing it can do is mark that the frame is a bad frame, and then it'll be dropped in the RX FIFO. So I might need to do some ruminating on this in terms of how to collect statistics properly, because naturally you don't want to count received control frames as errors, because it isn't an error. So we definitely need to differentiate between when a packet gets dropped because the receive FIFO overflows versus versus packets being dropped due to bad CRCs versus a packet being dropped due to it being a control frame. Well, that really shouldn't be counted as a packet drop because that was processed as a control frame. So there's a couple things I need to sort out at some point such that we can actually count this stuff up accurately. Let's see. And then for pause and PFC frame handling, pause frames and PFC frames are specified in the IEEE spec and a couple of the annexes. So pause frames, I'm actually going to call this, I think, in the logic link level flow control, or LFC. And then we have PFC, which is priority-based flow control. And the reason I'm going to go with LFC is then that differentiates between flow control messages and actually, pausing the TX traffic, for example. And also LFC and PFC, it's clear those two are related just based on the name. So hopefully that will make things a little bit easier to follow in the HDL. And I have seen a number of different drivers and NICs that use the LFC terminology for the link level flow control for referring to pause frames. So there is some precedent for that. Pause frame and PFC frames are used for building lossless Ethernet networks. They're kind of a component in that. I mentioned that a little bit before in terms of, they can be used to prevent congestion-based packet drops. So the idea is to prevent buffer overflow by, on the sync side of a link, you can request a source to stop sending either entirely or a particular priority for some period of time. So this uses a MAC control layer to exchange this information. On the RX side, what we need to do is extract the pause quanta values from the packets and keep track of those and drive the pause request lines accordingly. So the way both PFC and pause frames work is they contain pause quanta values. One pause quanta, I think, is 512 bit times. I should probably double check that, but I think that's right. So you have to make sure that, those counters are decremented appropriately to make sure that when you get a request to pause a link, it gets paused for the appropriate amount of time. So on the RX side, that's pretty straightforward. You just have counters. Every time a packet shows up, you update the value of those counters, and then you decrement the counters at the appropriate rate. When the counters are non-zero, you assert the pause request line going back towards the user logic, or in the case of pause frames, you could terminate that inside the MAC to block, new TX traffic. On the TX side, what we need to do is accept a pause request from something and generate frames based off of that, and also refresh that periodically. Because again, when you generate those frames, they will have pause quanta in them. So if you have an extended pause, you might need to send those frames periodically to make sure that the quanta doesn't run out at the receiver. And then again, when the pause is deasserted, you need to send a new frame with the quanta value of 0 to restart the flow of traffic. The quanta counters also need clock enables and adjustable step size to deal with different configurations of the MACs. So I know at least for SGMII, for example, it tends to always run at 125 megahertz, but then you have a clock enable that's pulsed either every 10 clock cycles or every 100 clock cycles to deal with the lower rates. So you need to be able to reflect that in the quanta counters to make sure that they actually track the appropriate 512 bit times per step spec. I also mentioned before that the pause frames, they can potentially be connected internally directly to stop TX traffic within the MAC, but PFC has to be handled deeper in the design due to the traffic classification part of it. So I'll probably be able to get pause frames working directly relatively soon. PFC is going to require some more modifications to some of the FIFOing infrastructure components. All right, in terms of how to implement this in Corundum, I think I briefly touched on two different things. One method is to integrate the support into the MACs. The other component is to use the L2 ingress and egress modules in Corundum. So the advantages of integrating into the MAC is, at least for a hard MAC, you save some logic resources, and the quanta step size should all be handled by the MAC internally and should always match the link rate. But the con is that for using the built-in MAC stuff, the configuration then becomes potentially quite target dependent, and then you'd have to probably manage that with a soft core, or maybe not support very much configurability. And then if you're going to use the L2 ingress and egress implementation in Corundum, the con of that is potentially a slightly higher resource utilization if you have a hard Mac that could potentially implement PFC. And you also may need to make some adjustments to the Quanta step size to match the link rate. You know, if you're reconfiguring link rate, potentially that would need to be adjusted, or we might need some additional connections. Haven't investigated that completely. But the main advantage is that it's going to be target independent. Doesn't matter what Mac is connected, doesn't matter what board you're running on, that logic will be the same. But there's another couple of other potential considerations as well. For latency, I'm assuming it's not going to make much difference depending on what you do, with the only exception I can think of being the E tile. If you're terminating pause frames on the E tile, then you don't need to cross the EMIB twice. But if you're using PFC frames, I don't think that matters because you do have to cross the EMIB twice effectively. So not sure if that really makes much difference. Either way, you're paying quite a bit of additional latency because of that EMIB crossing. And then another thing is, like, if you're not running with a Mac directly, but if you're connected to, for example, some sort of an embedded switch, maybe we don't need to send pause frames at all, but maybe we just need to interconnect some pause request lines. Not sure. But seems like there could be some reason to support using both of these depending on the configuration. So I'm probably going to start with the L2 ingress egress implementation and see if I can add some additional control lines that could be used to support either using hard Mac or an embedded switch. So that's about it in regards to that. And then just briefly, a couple of updates to Verilog Ethernet. I updated all the Vivado makefiles to use basically the same ones that Corundum uses. I also switched all the example designs. Any board that supports operation at 25G now has a unified 10G 25G example design using basically the same setup as Corundum, where the config.tcl updates the GT configuration. I'm working on adding the Mac control layer and PFC pause frame support modules. And then once we have those modules in there, then I'm going to integrate that into all of the Macs. And with that, then we should be able to do, well, once that's done, then I'll pull all that back into Corundum, and then we should be able to get at least pause support in the short term, PFC support in the longer term. So yeah, I'll definitely keep you guys up to date as I'm putting the pieces together for this. I think that's all I got for today. If anyone has any questions or comments, then fire away. Oh, does Julian, you can go ahead and ask. You don't need to raise your hand necessarily, unless I'm misinterpreting what that is. That's a raised hand, right? Yeah, if you have something to ask, just go
No,
ahead.
that was just an applause because you did a lot of things these days.
Oh, okay. Yeah, I'm just not wasn't sure. Was that a raised hand? Was that applause? Was that unfortunately
it was an applause
client is not giving me a little tooltip or something telling me what that is supposed to mean. So
okay.
Anyway, thanks.
Yeah. I think we are going to test all of that in the U50.
Okay.
In the next in this week.
All right.
So we
Sounds
might have
good.
a little more feedback at this time.
Right. Yeah. So I'm not sure how long it's going to take for me to get the pause frame integration done.
Sure.
Hopefully that'll be done within the next couple of weeks. At least the HDL side for actually handling the frames is looking pretty good. So that's hopefully won't take that long to integrate it. And I was actually starting to take a look at the driver side of things. I guess I can mention that real quick. It seems like the pause frame support is controlled via ETH tool, but the PFC stuff is handled by a different utility. I have yet to get my head wrapped around how that works. If anybody's familiar with the driver side for PFC and pause support and could shed any light on that, that would be great. because I'm just going through the source code for other device drivers to figure out how things are done. So
I think the actually what does the ETH tool, it's only it set flags in the driver, and it's the driver itself who do the work to program the card with the pose frame and all of that, but there is no active work from the ETH tool itself. I don't think so.
well, right, it's a question of which APIs do you have to implement in the
Oh,
driver,
oh.
right? Because ETH tool will have like get pause configuration, set pause configuration. It's like, okay, then you can look at the arguments for those and figure out what you need to do.
Yeah, that works through IOCTL, like the old way, and the new way is a netlink socket that the tool IP use.
Right,
And
but I think
in theory, you should be using the netlink interface for everything, but a lot of driver does not yet. So
so is it actually different APIs for those?
yeah, in fact, the IOCTL have
Interesting.
just raw numbers that you send with arguments, while netlink is really some kind of complex semantical complex message that you can exchange. And now the tool IP, you can use it to send a lot of different message to different layers, and some of them are catched by the card itself, and some other are more high level. Like for example, a good example for that is VLAN filtering. Either it's supported by the card itself. In this case, the netlink message goes down to the card to program the card for VLAN filtering. Or if there is no filtering in the card itself, then it's Linux who intercepts the message and does the filtering in software.
Okay, so it's kind of a much more general method for handling
Yeah,
all of this
exactly.
stuff, as
While
opposed to having 500 APIs, you just have a couple of APIs that hand these messages around.
yeah,
Interesting.
and
Well, so I guess
well,
one thing to differentiate between is what the user space implementation is and what the kernel implementation is. So I know from the user space you might have a different method for talking to this, but it's a question of what the kernel does with that. So does the kernel convert these netlink messages into calls to some of these APIs, or is there a different set of APIs you have to implement in the driver to handle these
yeah,
messages?
that's it. You register. You register, in fact, a netlink handler with a list of message you want to handle. And when the kernel see this kind, it's like a socket. In fact, it's called a netlink socket.
Right,
So
right,
it's
okay.
a specific type of socket. And when the kernel recognize that your card register one handler for one kind of message, then it forward it to your driver, and then otherwise it just take care of the issue itself.
Gotcha. All right. I'll have to take a look at that. Do you know
That
when the netlink support was added to the kernel approximately?
oh
Because I know is that like super new, or is that also supported
no
on
no
like
no
RHEL?
uh, it's very old, but at the beginning it was not used a lot,
I see. Okay.
and then they extended it more and more and more and more, and for everything and nothing. And so now it's getting very big, but on the user space you have some library to handle that, and in the kernel space you also have some help to do that,
Right.
some API.
I'm
So
almost
but
wondering if you have to kind of implement both, right? So if you're using like ETH
mm,
tool, does ETH tool ever use netlink APIs?
no, usually each tool is an alternative mechanism that can reach the same thing,
Okay.
but
If it's so it's using different entry points into the driver, I
yeah,
suppose, right?
exactly.
ETH tool APIs instead of netlink. Okay. Interesting. Yeah, I'm much more familiar with using ETH tool. I am gonna have to do some reading on
Yeah,
netlink. Interesting. Oh, I guess I was getting Netlink mixed up with DevLink. Okay. Because
Hmm.
DevLink, I think, is how you switch port types and split ports and things like that. So I thought, yeah, so I know DevLink is kind of operating on a different level than.
Yeah.
Well, I'll have to do some more reading on that. That's an interesting point. So this potentially has support for configuring pause and PFC and that sort of thing.
Yeah, it depends on how you program your driver. I mean, most of the older driver often have ETHLink for some things and Netlink for what is not supported on its tool. You know,
Okay, I see.
and
So,
and
okay.
most of the newest one are completely port on Netlink, but also have to maintain some kind of basic configuration compatibility with its tool, because of course there is a lot of script and all of that use that.
Yeah.
And so they have to support it. For example, for changing the speed, for the discovering the available speed and all of that, there is the basic stuff they need to support that.
Yeah, I just find it interesting that the kernel doesn't have some sort of automatic legacy ETH tool to Netlink conversion sort of thing, such that you could only implement the Netlink
maybe it
API.
exists. Maybe it exists. I have to check. I don't know. Maybe you're right. There is something like this, because it's quite complex. Because in ETH tool, you have some standardized calls, like for example for the speed or the type of connection there is, but there is also a lot of people that use that with specific IOCTL codes that are not standardized, and so in this case you cannot really do any emulation, because you cannot know what kind of argument is required.
Right. Yeah. Yeah,
So,
I've not done anything other than just look at the standard ETH tool APIs. So, but yeah, I guess that wouldn't surprise me that they have a mechanism for doing non-standard stuff, and that I'm sure people abuse that left, right, and center.
yeah, it's just IOCTL. So you have some kind of you have a number that you can pass for the operation code, and then you just pass a pointer with a size. So basically, you can do.
Gotcha. Yeah, so I guess IP route 2, it says there's a DCB tool which presumably would configure PFC. Yeah, maybe that's what it is.
IP root is a package where IP is stored
Yeah,
along
that's
the
IP,
library.
ADDR, IP link, all of that stuff
Yeah,
is IP route 2.
yeah.
So it helps to know what IP route 2 is, otherwise it's really hard to Google that stuff.
Yeah. I agree. It's not the best name ever.
Well, I mean, the it's more like the commands are very generic.
Yeah.
Well, and the name IP route 2 is just history. I mean, it started, the whole thing started with an alternative interface to the routing configuration of the kernel. And that's why it's called IP route. That's what I get.
Right, even
from
though it
there
supports a
they
lot more
extended
than
it
just
and added, yeah.
Yeah, even though it supports a lot more than just IP routing stuff. I know
Yeah,
it replaced some of the older commands for managing the link state, like ifconfig. That's right.
Yeah.
That's now been subsumed by IP route to IP link, I guess. Okay, so I guess that would make sense because I think the documentation I found before talking about the PFC support was probably doing something through either IP route 2 or It could have been some other utility, but I guess it must be using Netlink in the background to actually talk to the driver instead of instead of ethtool, because I don't think I was looking at the ethtool APIs. I didn't see anything that said anything about PFC. There were some mentions of pause frames, but not PFC. So interesting. Looks like we'll have to implement that one way or the other. So, all right, well, that's good to know. Well, does anyone else have any anything they want to discuss? I had a couple of messages back and forth with Leo, but we can always have a separate discussion on that stuff if you don't want to talk about it now.
Yeah, maybe it's because there's a lot of things that is still unclear. So I prefer to have cover in.
Yeah, sure. We can discuss that and set up a separate time slot for that.
Thank you very much.
I think he's shy because
Yeah, it's
My
understandable.
English is not
The English.
perfect, and I am afraid to say something really dumb.
Yeah, no worries, no worries. All right. Well, I guess we're just about at the hour here. If anybody has any other questions or comments, now is the time to fire away. Otherwise, maybe we'll go ahead and adjourn the meeting for this week. Nope, nobody. All right. Well, if anybody has anything that you want to talk about, we have the Zulip. More than welcome to post questions on there or GitHub issues or whatever. In the meantime, I guess we'll go ahead and adjourn the meeting for today, and we'll see all you guys in 2 weeks. And also, if you're interested in the Switch, we have those alternative meetings on the alternate weeks. So if you're interested in the Switch development, we'll see you next week. All right.
Thanks
Thank
for
you very
having
much.
me.
Thank you.
Thank you.
Bye.
All right. Talk to you guys later.
See you.